All right, everybody. Thanks for coming. So diffusions are kind of everywhere now. We've seen a ton of results and discussion about them so far, but I asked some of my students to just pull out a bunch of results that are at iClear in 2023. That's what these last ones are. And so we can see people are building small drug-like molecules, designing proteins, sampling 3D meshes from them. This might be the only real figure I'll have in the slide, so please take it all in while you're looking at that. But another aspect of diffusions is that they get good likelihoods. They're not just about producing samples that people like or samples that people find useful. They actually have been producing likelihoods or bits per dimension, or lower is better, that are as good or better than existing autoregressive models, which were the standard here. Okay. What is a diffusion model? The diffusion model is a model that takes in some noise prior stationary distribution sample and then maps it to something that looks like data. You can forget about the bottom arrow for now, but that's just the process of training it. And if we want to make that a little bit more formal, we have a model which samples from a prior, and then you take that sample from the prior and run it through a Ito stochastic differential equation. And I like data to be at time 0, but I like to integrate forward in time. So what we're going to do is we're going to say that the data itself is going to be Z0, which is the time reversal of this process that's up here. So you run this process until capital time T, Y of 3 minus little t is the time reversal of this process. Sometimes the statement that the data is time 0 is a lie, and you need a likelihood. And when you need a likelihood, we're going to say that you sample the data conditional on the SDES value at some time very close to 0. So epsilon you can think of as a number that is close to 0. So how do you train a diffusion model? There are lots of ways to do this. One way, if you were just thinking about it from other deep generative models, is to just train with maximum likelihood. If we train a normalizing flow with maximum likelihood, a VAE is a lower bound on the maximum likelihood objective. And this one here would really require a couple of things. You could either think about, hey, to compute the marginal distribution, which is what you need, this is the marginal of the observation, I can integrate out the stochastic differential equation. Alternatively, I can write down the time evolution of the actual density itself and try to solve this differential equation, called the Fokker-Planck equation or the Kolmogorov-Forward equation. But I want to say that just like for other generative models, there's not a single answer here. It's not like we're married to maximum likelihood. You can write down score matching and it has optimality properties. But if you go with me for a second and you're like, okay, I want to do maximum likelihood. Those two things that I just described, integrating out an SDE, solving a partial differential equation, sound hard. So maybe I can rely on one of the traditional tools that exist in training models that have leading variables. And that's variational inference. So what variational inference is you have the quantity of interest, which is the log probability of what you observe. You write that as an expectation under the prior of the likelihood. And then there's a step that I'm calling change of measure. This is not the typical way maybe you'd see these steps written, but change of measure is really saying, instead of having an expectation under P, I want to make it an expectation under Q. The value is the same. And then the final step is Jensen's inequality, where you're going to push the log inside the expectation. In a diffusion model, if we just sort of try to map things out, the data, if you humor me again, is going to be the x is equal to z0, forgetting about this like epsilon and likelihoods. And the latent variable really is the path of the stochastic process for all times greater than 0. And one immediate challenge here is that you kind of only know this quantity just like at the prior, at time capital T in the time reversal, or time 0 when you're integrating it forward time. And so you can't really just directly apply it. And the first result in people working in this area, and most of this talk, I should say, is like assembly of math. Like the results exist in some way and people are putting it together in a nice way. And we'll do one, but the first result is by Huang. And they're like, if we just take maybe the first couple of chapters from a book on stochastic calculus, we can just carry out the same steps that we do for the traditional elbow and do it for diffusions. And if you do that, you get an objective. This is a proper lower bound that is complicated. Maybe the only thing to pay attention to is there's a term that looks like score matching inside of it. So some of the properties that we would need to have a lower bound or to maximize lower bound would also be true if I'm trying to do score matching. The high level steps for carrying it out, if you were to like open the textbook and just do this, is the first step is you're going to write the partial differential equation for the marginal density. And that is this Fokker-Planck equation that I mentioned. The next step would be, well, I can't solve the PDE, but there's a connection between PDEs and SDEs, which is the Feynman-Katz formula, which will let me write the marginal density I care about as an expectation with respect to a particular SDE. And again, computing this expectation is like an actual path is difficult. So you're going to use change of measure, introduce another stochastic process Q, and use Jensen's inequality like you do in variational inference. There are a few other steps that are like mostly algebra. Choosing the model parameterization appropriately to get a score out is one of those steps. But basically, this is all you need. And it's like, if you open the textbook, it's like maybe 10 lines of math. And what do you need to do this? You would need to have the ability to sample from the transition kernel. To sample ZT given X. We see that is right here. There's an expectation on the inside. We want its score function. This is like a score in quotes, not maybe the score that you see in a statistics book. And you'd also want to have the approximation tend towards pi. You know, we want the stochastic process that we choose for inference to have a stationary distribution that looks like what we're going to start with from the model. And if we look at other objectives, if you looked at score matching, you basically have the same similar requirements on what you need to compute. So what type of inference processes, corruptions, noising can you use? The most common one is variance preserving. It's a scalar process that will tend to a Gaussian distribution. But you could, think more freely if you're thinking about this as a latent variable model. You can add an auxiliary variable to each observed dimension. And instead of running like the simple Gaussian system, you could run the critically damped Langevin system. Okay. The reason that you might do it, it's proposed in this paper from last year by Dockhorn, is you might say, well, the model that I'll end up with will be a lot smoother because the time evolution in this critically damped Langevin is going to look smoother. Sort of the argument they get. And so here's like, if you look at the appendix for the critically damped Langevin paper, there's a lot going on. It's like, this is just like 2 pages of it. There's many more pages of this. And you have like a lot of descriptions of the solution. You have some proof of correctness for the mean that is short. The covariance one is going on. It's like heavy, and that's just for like one specific inference choice. You could say, well, maybe these differences don't matter. Here we have what Yang Wen calls the toy data sets that we can use in probabilistic modeling. And we look at this variance preserving stochastic differential equation for inference and the critically damped Langevin equation. And we can see that the bits per dimension have different orderings on 2 data sets. So on the CFAR10 data set, the Langevin equation is better. On MNIST, variance preserving is better. The score models are basically the same. There are not many more parameters that are injected. So it's like a apples to apples comparison. And you'd be like, how many processes are there? Maybe I just have the variance preserving process and I have the critically damped Langevin equation. But Stefan,
I don't like where this is going, but I'll tell you later.
yeah, we'll see. Let's see where he's gonna go. I think you know where it's going. And you're like, they're really a ton. You can change the number of auxiliary coordinates. You can change the relationship between those. But like, if you want to try out each one, you're just gonna have to redo those calculations. And I don't like doing manual calculations. Like the more that the computer can do, like the happier that I am. Okay. And so our goal really is just to develop an automatic approach for even just linear inference, meaning that like the stochastic process for inference is linear in the variable that you're evolving. And so the first step that you need is just a multivariate evidence lower bound. This is not much more work than the original evidence lower bound. It's just like adding an extra auxiliary coordinate. You can see sort of the remnants of this auxiliary coordinate here. The other parts of it are hidden in the fact that the SDE is now over 2 dimensions. But we still have the same requirements. We have the requirement of Q. We need its gradient, and we need to have Q tend towards pi. So the first step that we're going to do, and again, it's like you take a textbook, you read it for several pages, is to just derive the automatic mean and covariance for the transition distribution. And the way that you look at it, you get a differential equation for the covariance. So this sigma t given 0 is the transition covariance to find the sampling distribution of the inference process at time t, given whatever initial state that you have. And you get this kind of funny looking differential equation, but you can actually solve this, and you can solve this using matrix factorization, meaning that you can write down 2 matrices whose solution are known in closed form. This is a matrix exponential, and this is a multiply right here. And then we can say that the covariance matrix is the product of CS and HS inverse. So in this sense, the covariance matrix is in closed form up to this matrix exponential. Then this is an explicit solution for the time varying case. This little a with the brackets around it is an integral. To compute this integral, you'll typically have a fixed matrix and a scalar function with a known integral on top of it, so you're not manually integrating a function. And the mean is similarly, it's actually quite simple to solve. And most of these results are in a textbook on stochastic differential equations. So this is the first part, we sort of have the automated transitions. And you can ask me, like, is this approach any slower? Well, if we just use the out-of-the-box matrix exponentials that are in PyTorch, not so much so. So we took the analytic calculation in the automated one, and this is, I think, 256, a batch size of 256, and you can see that the automated one is about 10% slower, not like crazy slow. For the stationary distribution, well, you know a lot about converging to a stationary distribution. Stefan is smiling. And so what you'd like to limit A and G so that we end up having this process CT go to something that's normal 0, 1. And there are like a ton of results on this. And specifically, what you can do is you can reparameterize this process in terms of a skew symmetric matrix Q and a positive semi-definite matrix D. And if you were to run this process for any choice of Q and D, then Q of ZT is going to have pi as a stationary distribution. Okay. And to sort of see how this comes from, well, you want a time varying extension of what's in Markov chain Monte Carlo. And these results in Markov chain Monte Carlo really come from physics a while before that. And so now we have like a automated approach. We have our diffusion elbow. The way that you can just train something up is you can specify a Q, specify a D, then Q automatically tends to pi just from the analysis. And we can use the closed form of the mean and covariance to compute the transition kernel and its gradient. And since stuff is Gaussian, if I know the distribution, I can sample from it. It's not true if I have an arbitrary complicated distribution. Okay. And so then we're like, okay, let's pull something out of the box. In the MCMC literature, there's a third order accelerated Langevin equation, you can show faster convergence with it than the second order version. We built just a modified version of it to train a model just to see what happens. And so we wrote down a Q matrix, wrote down a D matrix, and we get some numbers out added to this table. Maybe follows a similar trend where the MNIST results are worse, but the CFAR results are still better than the original variance preserving SDE. But there's still some thinking to do. How do you pick this specific diffusion? Like some of the thinking is like, you know, what Q and what D, what model you're training on top of it. There's an annoying point of actual like ergodicity where if you have the stochastic process, does it actually reach the distribution? If it's a stationary distribution, there's some question on uniqueness as well too. But with everything automated, you can just optimize it. And you know, I call this like putting the variational back in variational inference, where you know, these models are set up in a way, at least if you're looking at like lower bounds, you like fix the variational approximation, you train the model parameters, you open the textbook for variational inference, you're like, well, what I'm trying to do is like make my lower bound of the likelihood as good as possible, even for a fixed model. And this is like slightly putting it back. There are not actually too many free parameters here. But you can actually see some benefit for this, where if you move to the learned system, you kind of see that like, I don't really have to choose so much anymore. Like this number is better than the rest, and this one is pretty close to the best one that's here.
Sorry, what was K? I think I've lost it.
K is the dimensionality of the system. So in the critically damped Langevin, there's one auxiliary variable. In this modified accelerated Langevin, there's two auxiliary variables. And it's learned, we just had one, but the Q and D matrices are parameterized in the way that's learnable. For a skew symmetric matrix, it's like a matrix minus its transpose. For a positive definite matrix, it's like LL transpose. Kind of like another implication of this is like, you know, you might be like, hey, this is funny. I know that the time reversal of a process will give me tight inference. And if my score models are big enough, I should be able to do the time reversal. And kind of like, you know, this big enough is an abstract question. Like, are they big enough? Is there still a gap? Meaning that if you fix a class of score models, you fix the data distribution, is there a gap still for the specific process you're choosing? And kind of you can see something interesting here where like, if you triple the number of parameters in a score model, you can get similar performance to just optimizing your inference diffusion parameters. And it's kind of neat in that, like, at least for the batch sizes we're looking at, you probably need to go across multiple GPUs for a model of this size, while for this model down here, it fits in a single GPU. And really, it's I should say this out loud, it can aid in making these models more accessible. But there's lots to be done here. When you have simpler computation, you have new questions. We did variational inference in sort of the naive way. If you followed the variational inference literature for a long time, you might be like, once I start optimizing Q, I'm going to generate a lot more variance in my optimization. We kind of forget about that. There's a difference between reparameterization gradients and pathwise gradients that play a role. There are questions about what does nonlinear mean? Is linear making nonlinear feasible in some way? But this work is at iClear, and my two students did all the work.